is Chief Architect of Cisco. That's all he wants me to introduce. He's too known, so I think he doesn't need much more introduction. But in any case, Dave is known for his leadership in technology and the implementation. At one time, I know Dave was a IETF area director, routing area director. At the meantime, is a 4 working group chair. I had the pleasure to working with Dave for many years in Cisco and service providers. Dave, thank you.
Thanks, everybody. So as my slides appear, being at MPLS World Congress and having come here for many years, I actually wanted to talk about straight up networking today. And so I thought maybe we'd talk about how to engineer networks for what applications are trying to do on that network. And so a little bit different than the previous talks, but nonetheless, let's move forward. So what problem do I want to talk about today? The problem I want to talk about today is that an application's desire of what they want from the network is currently not expressed by our control plane, by our data plane, by any of the suite of protocols that we can debate about. And instead, with the constant emergence of a greater number of application developers, greater use of cloud and data center to deliver these services, how can we represent that more easily in the network, automating this as well as allowing the application to control what's going on in the network? Heresy, you say. So I want to get a couple things out of the way. Here's your SDN, NFV, orchestration, IoT, big data, analytics, control plane, data plane, open flows, and any other buzzwords that you want to have. That's that part of the conversation. But instead, looking at the stacks that you see behind me of the usual things, here's the problems with the network. Here's all of the responses of the buzzwords to solve these problems. I want to bring up a new one, which again is the fact that today applications are not interacting with the network and being able to utilize all the capabilities and services that exist in the network today. We do carry too much state in the control plane. There are many changes to reduce that state, but really the key here is that the network itself does need to become a platform, and application developers may or may not know exactly what they can do to the network, but we can represent that. We can represent that using some newer technologies. And so some of these specific pieces, and I think folks understand this well, you know, if we call basically the era that we've been in since IP optical have come together and the rise of MPLS over the last 15 years or so, we do have the ability to specify paths. We do have the ability to create not only shortest paths, explicit paths, bandwidth constraints, and specific pieces, but we do have to carry all that state in the network. We do have to, unfortunately, run into the scalability issues that Kriti just chatted about. And I actually do believe in what we'll chat about just in a second, is that when we begin to express the network in a different way as a platform, as something that can be modified by the application itself, we can begin to talk about engineering, or we can engineer the network for those application desires. And it is enabled by all of those technologies represented by SDN, automation, et cetera. So for example, again, we're going to go through a bit of brief history just for the sake of conversation. In the IP world, right, we could set up paths and we could set them up with QoS. We went a step further with MPLS where we were able to set up explicit paths, but still the impediment to the service desires of the network haven't been able to be represented by either of these technologies. Simply because, as we all know, when we set up label switch paths across the network, those are relatively static head and tail points across the network for a particular service. We attempted to manage application desires or service desires disjoint from the reactiveness that's possible in the network itself, and set up these relatively static paths. My goal, and certainly what I want to talk about today, is allowing the application to control how it utilizes the network. And so to be able to do this, there needs to be a way to bring together those application desires. Frequently, that software platform is an SDN controller, and we'll talk about that just briefly. But really what the focus of this talk is on segment routing, reducing control plane state and allowing the application to represent the path it would like to take across the network without adding complexity or state whatsoever to that network. And so to be able to accomplish this, interesting, my slides are moving up there, but not here. To accomplish this, the application itself defines what path or what capabilities it wants of the network itself. And it encodes that in the packet traversal, and that state is not carried in a control plane. So I've upgraded the old post office example or fish diagrams, and we're going to talk about luggage. And many of you may have lost luggage on the way here, but let's just give a quick recap of exactly how things are working with LDP that we all know so well. You want to get your luggage, or you're taking a trip from Seattle over to Berlin. And what you would do with LDP is, in fact, encode, okay, send it over and get it to Berlin. And by doing that, we basically end up sending it and having it follow a path that is going to be the shortest path by that LDP label tied to the IGP next hop as defined by Mexico. And it follows that shortest path over to Berlin. And so basically, there's no real control over that path by the application whatsoever. It just marked merely what segment it wanted to be put on. We upgraded. We've got RSVP. Kriti just mentioned it. With that, we're able to route the luggage to Berlin via Mexico and Madrid. And we're going to do that by, of course, carrying an explicit path directly across the network. Set up that tag, set up the label identifier, and off it goes. And it ends up reaching, by being looked up at each site, exactly how to follow that particular label switch path. Well known, we all lived with this with RSVP. Okay, so in contrast, instead of setting up these paths inside the network, either shortest path routed or via explicit routing, how can we represent this for an application to be able to encode this, that the network can pass this automatically? Well, that's what segment routing is in fact all about, where your luggage in this particular case, route it the same way, go to the same destination. You actually set it up that the application encodes what path it wants to take across the network and puts it at the source or at the head end of that particular path. And it's marked exactly how it's supposed to traverse the network without interacting with the control plane. Bringing this amount of specification or specificity to an application or to the application layer itself not only is performing traditional source routing, but at each segment across the network, and I'll define segments in a second, the network can make an independent choice as specified by the application itself. So the luggage heads off to Mexico, great, that's where it's following that particular label. We'll take off, we'll pop that label. Oh, look, the next one headed over to Madrid, great. We'll get the luggage over to Madrid, pop those two, and then it's going to take it off to Berlin. Remember, the point here is that the source of that packet, the application itself, define the traversal of that network and the capabilities. This becomes an extremely flexible and powerful concept when you continue to apply it into some of the use cases that I'll describe. So the pieces of this, really what I'm adding to this, to what Kriti mentioned before, is this is segment routing is running on existing MPLS forwarding planes without change. And it's also been extended to be able to work with IPv6 for IPv6 only networks, in which all of the functionality of MPLS can be brought into straight up IPv6. The control plane itself, when you add an application platform like an SDN controller to the network or a WAN controller, you have the ability to provision or to control the head and tail as well as the segments that application traffic is going to traverse. And it gives you complete path options for either handling shortest path or by explicitly routing across the network. The state is carried in the flow. The expression of the intent on the network is carried with each packet. That's what's fundamentally different than in the past. That specification is defined potentially by the application itself. So just cutting this back to basics, we're going to get off the luggage system for a second. Segment routing is about defining at the head end of an LSP or the head end of a flow what you want to have happen on that network. And so what's the definition of a segment? Well, actually, it's been defined such that that traversal across the network can be associated with IP prefixes, with direct adjacencies, with peers, and I'll walk through this directly. So as mentioned, you can define a particular segment to an IP address if that becomes the identifier associated with the endpoint that you want to be able to use. It can also be a specific IGP adjacency or a link between two routers. So again, you're building up that not only is it associated with IP prefixes, then with adjacencies, it then can be also associated with a BGP prefix. To be able to get it from a data center, as Sunil talked, using BGP in this particular case, you can start to pick egress points or multiple egress points out of that data center onto the WAN itself. And then, as I mentioned before, it can be associated directly with a specific BGP peer. And so by building up all of these different capabilities and the application having a platform to be able to program this into the network, the application or the service itself can completely define what it wants from the network without interacting with a heavyweight control plane or certainly with an OSS or management system. When you add in a WAN controller, and this becomes very, very interesting because what we did learn from SDN, certainly from the SDN movement, I'll call it that, was that a logically centralized view of the network itself is extremely powerful when trying to place load on the network. What I've added to the picture are extensions that we've worked on as a community called BGP Link State, which merely takes all of the IGP information and LSP information, whether pseudo-wires, traffic engineer tunnels, or VPNs, and pushes them out of the network. So the WAN controller now has a real-time weather report of what's going on the network. That WAN controller is the application platform that an application can request, please place my traffic on the network, please place my traffic or load on the network here, there, to that peer, to this prefix, or following this particular path. Because in segment routing, remember what I just said a couple minutes ago, you're programming the head and tail of the network explicitly. And that's what's fundamentally different about the way that we've done MPLS in the past. That end-to-end path that an application could specify, I've lost all my religion about southbound protocols. OpenFlow does some stuff well, NetConf does stuff well, path computation element stuff does well. I love them all. And they all do very specific functionality extremely well, and I refuse to have a unified SDN protocol theory of the world because many of us in this room have spent a lot of our careers trying to take every feature we ever thought of and shove it into our favorite protocol. And that hasn't gotten us as far and as fast enough as we've wanted to. So I'm more than willing to have the southbound interface between a controller and the elements itself completely evolve as necessary over time as we invent new functionality versus saying one protocol is better than another. No, things do things well. But, sorry, Kriti, I think I just answered a question that you got. On the WAN controller itself, what becomes interesting is the application not only can specify the path it wants to take, it can specify the end-to-end path across the entire network itself, as you can see in this green line. You can easily control equal cost multipath across the network, which has been a challenge for us as a community. We can easily control how to do inter-autonomous system or inter-domain MPLS or segment-based routing, which has been a challenge for us as a community. We put a lot of burden into the control plane. We had specific prefix leaking we had to do. And it was a metric pain in the neck to go actually even between IGP areas and get to the ultimate either router, switch, port, or prefix we wanted to get to because we always summarized in those areas. Now the summarization at those area boundaries don't matter. I am able to specify that path to the ultimate IP address endpoint without worrying about the aggregation that might have occurred inside a domain or inside an area. So as we do this, really what we're doing is we're binding the traffic onto that particular path. and we set up, and what ends up happening is we do set up for the particular case we're looking at. For example, in this case, we want a low latency path to 7 for this particular application. We have a real-time weather report of the WAN, including delay, jitter, packet loss, utilization, reserve bandwidth, the basic variables that are necessary to understand where you can send traffic and it'll meet an SLA, and you can encode that into a packet and have that traverse the network to be satisfied by that particular low latency demand. Rinse and repeat with some other simple cases. You need a certain amount of bandwidth between two particular points. You see that in the controller from BGP link state and that data being pushed out of the network in real time. That's encoded directly at the time of sending that flow or adding that load onto the network when the application's going to send it. And it can traverse the network again using equal cost multipath and follow that directly. We're certainly able to handle the automated fast reroute case and with local repair as well as with path repair. But with local repair, it's outstandingly easy simply because within this topology, remember, in addition to passing IP addressing associated with adjacencies and links and flooding those throughout the network, you're also flooding segment identifiers. And those segment identifiers, can be something in v6 or it can be a label itself associated with those adjacencies. It's a simple addition to the protocol itself that takes state and protocols out of the network, like RSVP and LDP, but adds that full end-to-end path visibility that's necessary. So what becomes interesting when you start taking a look at a couple complex cases that we haven't been able to solve easily with MPLS. And one certainly was, I want to specify the data center edges and have multiple exit points out of a data center that can give me a certain amount of bandwidth. I actually can do that by programming, again, at the input of the load into the network from an application or virtual appliance sitting in that data center and specify the segments that the application would like it to traverse to meet that bandwidth, which includes equal cost multipath out of multi-points of a data center. This was extremely challenging. Most data center diagrams look exactly like a pyramid and have a default route sitting to say, hey, the only way you're out of this data center is through that data center interconnect to that gateway router. And having multiple exits were extremely challenging. And thankfully, that's been removed. In addition, when we continue to push this up, when we want low latency for a particular application, by seeing what's going on in the network on that controller and programming at the source how that traffic is going to traverse that network, it will meet that SLA. And when we take a look at, we want to be able to have a service chain associated with going through multiple virtual network functions, we have the ability to encode that directly into the packet as well. And be able to have that traverse, in this case, go to the virtual network function hanging off 14, then take a pit stop at the virtual network function hanging off node 6, and then go on to 7. So these are some basic functionality that I first wanted to cover just on how do we maintain exactly what we have with MPLS and then go beyond that functionality, but certainly being able to do fast reroute, explicit paths through the network, but then solve some of the problems that have been challenging without the overhead of what we've had to do to manage the network. So without a doubt, straight up VPNs and service transport at one particular site to another, encode that segment directly into the packet without using LDP or RSVP-TE. We didn't have to signal those pieces. We didn't have to bind the labels to next hops because we passed the segment identifiers with the IGP. We passed the identifier with the next hop itself. Continuing forward, it actually does work with LDP. And it does have direct integration where you set the segments up to where you can pick up an LDP label as well. So this isn't an either-or set of technology. You have the ability to have within a network an incremental deployment where there's segment routing and then bind it into certain domains where traditional MPLS is still running. Fast reroute, as mentioned, associated with segment routing is certainly possible because we know the adjacency segments for local repair on the node itself. They have been flooded with the IGP. So in this particular case, again, without explicitly having to set up the control state of what that backup path is going to be, we were able to handle local repair. Traffic matrix collection really isn't an issue because we're able to, automatically count associated with those segments and associated with those paths, and understand who pushed that label on as well. So we get the traffic matrix from the head end across the network to the tail directly by deploying this technology. And then on a per content or per service or per application basis, we can engineer specifically based upon the application requirements that path within the autonomous system to the selected router, to the selected peer, and therefore, again, even based upon specific content out of a CDN network or applications out of a specific data center, it can be directly encoded into the flow. So just taking a look at a couple quick examples on this. Low latency path to 7 for one particular application, and build this out across the network. This can be handled and programmed directly into the WAN controller. That's going to learn and understand where the ultimate path segment is going to end up. Grab that segment ID, and be able to program that path across the network, head and tail, even across these borders, which traditionally was not possible. So now what I'm trying to describe is that an application in a data center has the ability to interact with a WAN and get not only the bandwidth it's looking for, but get the delay and jitter to traverse that WAN and meet the requirements ultimately that the application has to provide. And so then back in the data center, it's going to be able to push that path as programmed or as given that information by the WAN automation controller or by the WAN controller itself. What becomes interesting is when you begin to add multiple applications, obviously, out of the data center, where an application wants to send traffic different ways for specific endpoints. Building up this in real time on the WAN controller, we can actually program these different paths stepwise through the network, one way for low latency in the network, and then a different way for different requirements that were necessary. The key thing to remember is that these flows actually, and the application's specificity can go into the millions. There's no midpoint state in the network because we aren't programming the state into the network. We're simply adding the path segments to be followed at the head end, and the application defines this and it traverses the network. And so the scalability of this solution in engineering networks using a traditional MPLS forwarding plane or an IPv6 forwarding plane has a much, much higher level of scale and much higher level of programmability that was there in the past. So as I mentioned, the traffic engineering capabilities that are available in segment routing, for the first time, we're actually potentially removing protocols from our MPLS control plane, simply by moving this information into the IGPs. No doubt reducing the operational overhead, but in particular, as discussed by Karidi, massively reducing the amount of control plane state that needs to be in the network, as well as at any midpoint, which frequently wasn't actually interacting with the head or tail end specifically. By building in native equal cost multipath, this is additional functionality that right now is quite challenging in MPLS. And then whether we're looking at distributed computation or centralized, it just depends exactly how you want to view this. I'm a fan of dynamic routing without a doubt. I'm a fan of dynamic routing to be able to provide and flood information efficiently across the network, across multiple nodes, and have the fastest possible repair for fast reroute. But by adding that logically centralized view, I now have that application platform to be able to program paths directly across the network. The next piece I'd like you to remember is that this isn't just a WAN technology. This is capable to be used within a data center, federating data centers together, and signaling applications or virtualized network functions or those service chains that are sitting in a data center to provide network infrastructure functions but allow the network and the data center to be seen both as directly part of the network and engineering both at the same time. The next key piece is that this isn't just visionary, hey, let's talk about where MPLS is going. No, in fact, segment routing itself is being deployed today. And many of the talks that you're going to hear about tomorrow, you're going to see that it's multiple segments that are taking advantage of reducing the operational overhead, adding scale, and adding programmability of application specificity to the network. So the basic goals that I think are enabled by this technology, there is no doubt. Lower resources necessary. There's lower state necessarily in the network. There's definitely reduced operational overhead as we're actually removing elements from our control plane. And then because we're able to have application specifying the traffic engineering or the application specifying the engineering of the network itself, SLAs now can be built directly on those applications or on content or on the services being delivered. So the major markets and major segments, that we're going to see deployments of segment routing actually are fully across where we see the MPLS network. And in fact, bringing MPLS into the enterprise network where the operational overhead was considered a very high burden, segment routing actually has been taken on as one of the ways to get, again, application specificity directly represented in the paths and the utilization of the network itself. So I encourage you all to take a look at or listen to the talks that are happening tomorrow on this technology. You're going to hear a number of operators and providers and enterprises talking about how they're using it. So I thank you very much.
Thank you, Dave. Questions? Any questions for Dave?
Crystal clear at 100 kilometers an hour.
Okay. Actually, I think it's very interesting, today's session with the keynotes, all different aspects. I kind of think we're in the 50 grade of shade. So there's a traditional routing still going on. We're using them today at the network in all networks. We are also having the source routing with the IGP, BGP distributing labels. We're also having the other extreme, saying how do we set up all possible paths to be able to traffic engineer to distribute label with help of traditional routing or without. So we're also going to talk tomorrow how to scale large-scale data center. Thank you, Dave. Thank you, everyone. This concludes our session. Afternoon starts 2 o'clock. Lunch upstairs.
Thank you.